Okay, so this is the third lecture. Uh, in this lecture, we're going to use the axioms of probability to analyze a specific kind of probabilistic model, which is the easiest to analyze and is also the most frequently encountered in applications of probability. So I'm going to use the phrase probability space to refer to the complete apparatus characterized by the axioms of probability. So a probability space has three kinds of data. It has the underlying sample space with all the various outcomes. It has all the possible events that you can find as subsets of the sample space. And then it has the probability function, which tells you the likelihood of any event. So a probability space is just a mathematical phrase for a probabilistic model that fits the axioms of probability. Okay, so the particular situation we want to focus on in this lecture is a probability space in which all outcomes are equally likely. So this is what we refer to as a uniform probability space. So, hopefully this phrase should be easy to remember because the word uniform has this connotation of equality or same probability for different outcomes. All right, so let's use the axioms of probability to understand the consequence of making a hypothesis that all outcomes in a probability space are equally likely. So let's say we have a sample space omega, big omega, with n outcomes. And then for each outcome, little omega and big omega, we want to consider an event consisting of just that single outcome, little omega. So we have this sample space, and an event can be any subset of the sample space, but we can think of these kind of atomic events which have only a single outcome that qualifies under the condition or property defining this event. So we're going to use this notation where we put little omega for an outcome in set delimiter brackets so that this refers to an event with just the single outcome little omega in it. And we're going to assume, as I mentioned, for this first analysis of a probabilistic model, that all outcomes are equally likely. Okay, so decomposing the sample space into atomic events like this has two pretty clear consequences. First of all, if you have two distinct outcomes, then the corresponding one outcome events are mutually exclusive. Their conjunction is impossible because there's no outcomes in common between these two events. It's kind of overkill to even say that because there's only one outcome in each event and they're different. But, we can think of that as saying that these two events are mutually exclusive. So another thing we can think of is that if you take the disjunction of all of these atomic one outcome events, you get the entire sample space. It's just saying, well, I can reconstruct all the possible outcomes by piecing together each of these individual one outcome events. Okay, so now we can start using the axioms. So if you look at the chain of equalities I have on the bottom of this page, we start off with the axiom of certainty, which says that the probability of the whole sample space is 1. And then we can use our decomposition of the sample space into atomic events to say that the probability of the whole sample space is equal to the probability of the disjunction of all the one outcome events. And then since we know that one outcome events are mutually exclusive, we can use the additivity axiom to turn this disjunction symbol into a sum. So instead of looking at the probability of the disjunction over all outcomes in the sample space, we can look at the sum over all outcomes in the sample space of the probability for each of these one outcome events. And then we can use our hypothesis that all of these events are equally likely to say that the sum of their probabilities is just n times the probability of any particular one, because we have a sum where all of the numbers are hypothesized to be the same, and so the value of the sum is the number of entries in the sum times the value that was hypothesized to be common among all the entries. So we can see that this framework, where we assume all outcomes are equally likely, forces us to conclude that the probability of any individual outcome is 1 over n, where n is the total number of outcomes in the sample space. Okay, so now I'm going to rewrite. So what's on this page is at the top is just a change of notation. So the first two sentences on this page are just a change of notation that is going to make things more convenient going forward. So if we have a finite set S, we'll use the vertical bars on either side to refer to the cardinality or size of that finite set. And so if you look at what we did on the previous page, we made this hypothesis that the size of the sample space is n, and came to the conclusion that the probability of any individual outcome is 1 divided by n. And so all we're doing in these first two sentences is just substituting the notation size of omega for n, which was the number we assumed to be the size of omega. Okay, so now we can do pretty much the same thing as we did on the previous page for any particular event. If we consider an event in a uniform probability space, we can decompose that event into a disjunction of its constituent one element, or its constituent one outcome sub-events. So we can think of this event as the disjunction of all its sub-events, where we're again breaking everything down into atomic one outcome events. And so we can say that the probability of the large event A is the probability of its disjunctive decomposition into one outcome events. And then again, using the obvious fact that distinct one outcome events are mutually exclusive, we can turn the disjunction symbol into a plus symbol and say that the probability of the disjunction of all the one outcome events in the big event is the sum of all the probabilities of one outcome events in the big event. And then we can use the calculation from the previous page where we say that, well, a one outcome event in a uniform probability space has a probability which is the reciprocal of the size of the probability space. So we can substitute in 1 over the size of omega for the probability of each of these one outcome events. But now we have a trivial sum where we're again just adding up the same number over and over again. So we're adding up the reciprocal of the size of omega as many times as there are outcomes in the event A. So this sum has A different terms in it, or this sum has a number of terms which is equal to the size of A, and every entry in this sum is equal to the reciprocal of the size of omega. So this works out to saying that the probability of A is the size of A divided by the size of the total sample space. And so what we've done here is use the axioms of probability to derive the simplest of all formulas for calculating probabilities of events. If you have a uniform probability space, the probability of any event is the number of outcomes in that event divided by the total number of outcomes in the probability space. And you can see in the teal highlighting here, I have that written in mathematical notation as the size of A over the size of omega, and I have it written in a slightly more linguistic way as the number of outcomes in the event over the total number of outcomes. And, ideally, this uniform probability formula is something that you definitely want to stick in your head. The best way to do that would be not only to just memorize it, but to really try and remember why the hypotheses about uniform probability spaces allow you to derive this formula. But, you may at sometimes want to use this formula in mathematical symbols as size of A over size of omega, or sometimes you may want to use this formula just as more of a heuristic memory thing where you're writing outcomes in event over total number of outcomes. Okay, so we can see an initial example of how we can analyze uniform probability spaces. So in a course on mathematical probability, standard gambling games are an extremely valuable source of examples. And, if you grew up in a culture that doesn't play the same gambling games as are common in the US, that might be a little bit of a disadvantage if you're not especially familiar with how these games work. So hopefully it should be easy to research these kind of simple probabilistic games like throwing dice or dealing cards. And I'd suggest if you're not familiar with American dice games or card decks, just kind of do a little bit of Googling and try and figure out how they work so we can use them so we can use them in the course. All right, so we're going to have a problem where two fair dice are rolled, and we ask what's the probability they add to 7. So the first key word to look at here is the word fair. So in probabilistic modeling, the word fair is a key that you're looking at what a mathematician would think of as a uniform probability space. So when we say that the dice are fair, that means we're dealing with a uniform probability space. Okay, so we want to use the uniform probability space formula to do our calculation. And like always with solving probability problems, you need to figure out how to collect data from the hypotheses in the problem, arrange it into an appropriate formula, and then do the calculation. So let's look at our formula. We need number of outcomes in event divided by total number of outcomes. So for doing uniform probability space questions, I always suggest counting the total outcomes first, just because counting the total outcomes is usually easier than counting the outcomes in your event, and it gives you a sense of what's going on with the experiment that can help you with the more difficult task of counting the outcomes in the event. So let's think, what's the total number of outcomes for this sample space? Well, there's 6 outcomes for rolling one dice, and so the principle of successive experiment tells us that there's 6 times 6 total outcomes for the combined roll. So we get 36 total outcomes as the size of our probability space. So now we have to count the number of outcomes in the event we're interested in, where the 2 dice add to 7. And so usually we'll use more sophisticated counting techniques like binomial coefficients and that kind of stuff, but because this is the first example we're doing, it's just easy enough that you can count the outcomes in your event by listing them exhaustively. So we can see the various outcomes that add to 7 are: first is 1, second is 6, first is 2, second is 5, first is 3, second is 4, first is 4, second is 3, first is 5, second is 2, and first is 6, second is 1. So we've counted 6 outcomes that give us the event we're looking for, where the dice add to 7. So now we can apply the uniform probability formula, outcomes in event over total outcomes, and we get 6 over 36, which is 1/6. And so my suggestion is that if you have a problem in this course or later on in your life, if anyone ever asks you for a probability, your final answer should be a decimal with 3 significant digits. That's my rule of thumb. I'm not claiming it's going to satisfy everyone who ever asks you for a probability, but it's a pretty standard thing that if someone asks you for a probability, you should give an answer with 3 significant digits. So here I'm approximating 1/6 with 0.166. And, as a theoretical mathematician, I feel obliged to put these wavy equal signs instead of a hard equal sign just because, my mind interprets a hard equal sign as a hard equal sign, and 1/6 is not precisely equal to its 3 significant digit truncation. But, I'm leaving the exact rational number solution here because it's easy to write down. But for more complicated solutions, the exact rational number answer may have 20 digits in the numerator or something, and so your final answer usually will just be a decimal with 3 significant digits. Okay, so let's try and have a look at a slightly more complicated example that we can do for let's try and have a look at a slightly more complicated example that involves counting using a more sophisticated technique than merely listing out all the events or listing all the outcomes in the event you're interested in. Okay, so a committee of 5 is to be selected from 6 dogs and 9 fish. If the selection is made uniformly at random, what is the probability of the committee having 3 dogs and 2 fish? So here the keyword uniformly at random is again a common expression that mathematically refers to the model of a uniform probability space. So from time to time in ordinary language, people will use the word random simply to refer to uniform probability spaces. If in serious scientific contexts, people will always be more precise and say something like uniformly at random or fairly at random or fair choice or something like that, which connotes the idea of equality between outcomes. But if you see someone using the word random and it's not obvious exactly how they want you to interpret that mathematically, a standard thing to do is to interpret it as referring to a uniform probability space. But in this course, I'll always use either the words uniform or fair to indicate that we're talking about a uniform probability space. Okay, so the uniform probability space formula needs us to count 2 things. It needs us to count the total number of outcomes in the event, and it needs us to count us to count the total number of outcomes in the sample space, and it needs us to count the outcomes in our specific event that we're interested in. So, like I said before, I always suggest doing the total outcome count first because it's usually easier and gives you a sense of what's going on. So, what's the total number of outcomes? Well, we have this division of our candidates into dogs and fish, but if we're doing the total number of outcomes, we don't really care about the division into dogs and fish. We're just trying to see how many committees can we make if we have no further restrictions on the structure of the committees. And so in that context, the distinction between dogs and fish disappears, and all we're doing is choosing 5 things from 15 things. So we're choosing 5 things from 15 things if we don't care about any other condition on the event, and so there's 15 choose 5 total outcomes in our sample space. Okay, so now let's look at the event we're interested in. So the event we're interested in has 3 dogs and 2 fish on the committee. So if we're trying to fill in 3 of the spaces with dogs, how many ways are we allowed to do that? Well, there's 6 dogs and we're filling 3 spaces with dogs. So there's 6 choose 3 ways to fill the 3 spaces with dogs. And then we want to fill the 2 other spaces with fish, and there's 9 fish we can be choosing from, so there's 9 choose 2 ways to fill the fish spots on the committee. And then the principle of successive experiment tells us the number of ways to do both of those things is 6 choose 3 times 9 choose 2. And so now we have all the data we need appropriately collected and explained, so we can plug it into the uniform probability formula and do outcomes in event over total outcomes. And we get 240 over 1001. I've written that as a rational number because it's pretty short. The numerator and denominator are pretty short, but again, the final answer for a probability should always be an approximation to 3 significant digits with a decimal. Okay. So let's look at an example that's a little bit more sophisticated. So let's say we're dealing a deck of 52 cards to 4 players fairly. So the word fairly here is your clue that we're dealing with the uniform probability space model. And so the question asks us, what is the probability that each player gets 1 ace? So there's 4 aces in the deck, and we're trying to figure what's the probability these 4 aces get dealt 1 to each player. Okay, so since we saw the word fairly in the question, we know that we're supposed to approach this as a uniform probability space, and that requires us to do these 2 counts, total number of outcomes and outcomes in events. So we start off doing the total outcomes count, and what we need to think about here is the number of ways to distribute 52 cards equally between 4 players. And so we had these multinomial coefficients which told us the number of ways to divide objects into various groups. That wasn't quite the interpretation of multinomial coefficients we had originally. The original interpretation of multinomial coefficients we had was in terms of arranging groups of colored spheres in a line. but if you look at the connection we made between the two interpretations of binomial coefficients with arranging colored spheres and choosing objects, there's exactly the same connection which can be made between multinomial coefficients as counting arrangements of colored spheres and multinomial coefficients as counting ways to divide or something into groups or to choose groups from a total. So what this multinomial coefficient 52 choose 13, 13, 13, 13 is doing is this is telling us the number of ways to divide. Maybe divide is too much of a arithmetic word. I'll use split. Split 52 into of 13, 13, 13, 13. So binomial coefficient n choose k is the number of ways to split n into a group of k and a group of n minus k. And so the multinomial coefficient so a multinomial coefficient with two things at the bottom is exactly the same as a binomial coefficient, and these larger multinomial coefficients are playing exactly the same role of counting the number of ways to split a large group of objects into constituent subgroups. So we can count the total number of deals as 52 choose 13, 13, 13, 13. All right, so now let's do the more complicated task of figuring out how many of these outcomes actually qualify for our event, where we're interested in seeing one ace given to each player. So the way we're going to think about this is to say that let's first just distribute the 4 aces equally among the 4 players. So there's 4 factorial ways to do that. You have these 4 distinct aces, and you're giving them out to 4 players, which is the same as arranging 4 distinct objects in a line. So we get 4 factorial ways to distribute the 4 aces to the 4 players. All right, now once we've distributed the 4 aces to the 4 players, we're left with 48 other cards, and we need to distribute them as well. So given that each player has 1 ace, each of them needs to receive 12 more cards from the 48 remaining. So once we've distributed the 4 aces to the 4 players, we have this multinomial coefficient 48 choose 12, 12, 12, 12, which counts the number of ways to distribute the other cards among the players. So we use the principle of successive experiment to say that we've analyzed the event we're interested in as a distribution of 4 aces in 4 factorial ways, followed by a distribution of 48 choose 12, 12, 12, 12. So we count 4 factorial times 48 choose 12, 12, 12, 12 as the number of outcomes in the event we're interested in. And so Wolfram Alpha knows how to interpret multinomial coefficients. I'll leave it up to you to research in the documentation how to input a multinomial coefficient as opposed to a binomial coefficient, but to give you a hint, it's pretty much the same. You just say n choose k comma m. But so you can type this into Wolfram Alpha, and these numbers 52 choose 13, 13, 13, 13 is unimaginably gigantic. I have no idea. It probably has like more than 10 digits. Probably not as many as 20, but I don't want to write out a rational number with 10 digits in the numerator and denominator, so I just read off what Wolfram Alpha gave me as a decimal approximation to this probability, and I got 0.106. All right, so now let's do a problem that analyzes uniform probability spaces with a little bit of a different perspective. So instead of calculating a probability, we're asked to calculate a natural number. We're asked, how many people need to be in a room to make the problem of sharing a birthday at least one half, assuming their birthdays are distributed uniformly at random? So this is a very famous example in elementary probability theory. It's sometimes referred to as the birthday problem. If you've ever heard of the birthday conflicts in hashing or cryptography, that's exactly referring to this issue with people sharing birthdays in a room. But anyways, so we're asked to figure out, if we're thinking of people as just abstract entities being assigned birthdays uniformly at random, how many people need to be in the room to share the probability, or for the probability of two of them sharing a birthday to be at least one half. Maybe I'll make the wording of this question a little more explicit and stipulate that I'm only looking for two people to share a birthday. Okay, so I saw my key phrase uniformly at random here, which tells me that I need to be thinking about a uniform probability space and approaching things from the point of view of doing my total outcome count, my event outcome count, and taking the ratio. So we'll do the total outcome count first. So because we're looking for an unknown natural number n, which is supposed to tell us the number of people that need to be in this room to make a certain probability greater than a half, I'm going to use this variable n in my analysis of the problem. So if there's n people in the room, then, well, how many arrangements of birthdays are there? There's 365 choices for the first person, 365 choices for the second person, 365 choices for the third person. So you just multiply all those together, and we get 365 to the nth power as the number of arrangements of birthdays for n people. And so I'm ignoring the phenomenon of leap years just because it's not relevant to the math of what we're doing. So the total number of arrangements for birthdays is 365 to the power of n. So we want to figure out what's the number of arrangements where two people share a birthday. And if you start thinking about that for a little while, you'll come to the conclusion that it's actually easier to count the number of arrangements where nobody shares a birthday. Because you can count it like this. You can think, all right, if I have one person, then there's 365 choices for their birthday. Now, the second person, assuming they're not allowed to share their birthday with the first person, that leaves them 364 choices for their birthday. Now, assuming the third person is not allowed to share the birthday with the first two, that leaves them 363 choices for their birthday. And so we go on counting down like this, where each time we subtract one more possibility from the number of birthdays that are available, assuming nobody shares anything. And so we started off subtracting 0, and then we subtracted 1, then we subtracted 2. So ultimately, after we've taken into account all of the n people in the room, we're going to see that the last term we need to consider in this product is 365 minus brackets n minus 1, because we're counting off n people, except we have a shift because we didn't subtract 1 initially because the first person was allowed to have any birthday they wanted. So since we didn't subtract 1 for the first person, we end up subtracting n minus 1 for the last person instead of subtracting n. And so if you think about this expression, 365 times 364 times 363, all the way down to 365 times n minus 1, you can see that an easy way to express this quantity mathematically is 365 factorial divided by 365 minus n factorial. Because, okay, let's try and think about what happens when you do the ratio of these two factorials. Well, the numerator starts off with the full product from 365 all the way down to 1. And then the denominator has this partial product that starts at a lower number, 365 minus n, and goes all the way down to 1. So when you take the ratio, all that happens is the denominator cancels exactly the tail of the numerator that you want, and you're left with the initial segment of the numerator you were looking for, where you have the part of 365 factorial that stops at subtracting n minus 1. Okay, so now what have I been able to do? I've been able to count the number of arrangements of birthdays I've been able to count the total number of arrangements for birthdays for n people, and I've been able to count the number of arrangements where none share the birthday. So using the uniform probability formula, I know that the ratio of these two counts is the probability that nobody shares a birthday. So you can see on the next line, I have this ratio written in large parentheses. I've written 365 factorial over 365 minus n factorial divided by 365 to the power of n. And so that quantity in parentheses is my probability that I've calculated for this question. I calculated that probability as an application of the uniform probability formula where I still have a little bit of abstraction with my unknown variable n. And then I think, okay, this quantity in parentheses is the probability that no one shares a birthday. I'm interested in the probability that some pair actually does share a birthday. So last time we figured out that if you want to calculate the probability that something doesn't happen, you do 1 minus the probability that it happens. So what I'm trying, okay, let me take stock of where I am. I have this ratio in parentheses, which I applied as the uniform probability formula to calculate my probability that nobody shares a birthday. And then I'm doing 1 minus that to calculate the probability that a pair of people actually does share a birthday. But maybe the word calculation is still not quite right here, because I have this unknown quantity n, and I'm not so much calculating as trying to solve for n. So what I end up wanting to figure out is what value of n makes 1 minus this ratio greater than a half. Because the question asks me for what value of n makes the probability of sharing a birthday greater than a half. And I've set up this expression in such a way that asserting 1 minus this quantity is greater than a half is mathematical language for asserting that the probability of sharing a birthday is greater than a half. So, to be honest, I haven't the slightest clue how to solve this equation for n, or how to solve this inequality for n, but luckily, artificial intelligence can approximate an integer solution. So I'm going to type this into Wolfram Alpha. If you type this into Wolfram Alpha yourself, you need to be careful with putting parentheses around everything correctly to make sure that it's understanding what you want and getting all of the ratios collected in the way that's suggested by the mathematical notation I have here. But as I was talking about in the interactive lecture on Monday, the great thing about Wolfram Alpha is it will always show you an standard mathematical notation for what it thinks you meant, so you can make sure that it interpreted your parentheses and expressions correctly. So I typed this into Wolfram Alpha with the caveat that I figured out exactly how to parenthesize it correctly and ensured that it understood my parentheses correctly, and I asked it for an integer solution. And it gave me a list of integer solutions, and the least entry in this list was 23. So I'm going to say that 23 is the minimum number of people needed in a room to share a birthday. And so this little probabilistic model we've analyzed here is often considered counterintuitive, because if you ask somebody who doesn't know anything about probability how many people need to be in a room to share a birthday, they'll probably choose an answer which is really close to 365, because the only way to be absolutely certain that two people share a birthday is to put 366 people in a room. But I guess the kind of philosophical message from this analysis is that even though you need 366 people to be absolutely certain, to get a probability of a half, you need way less than half of 365. You only need 23. Okay, so I'll end this lecture there.